Somewhere in the constellation Aquarius, 39 light-years from where you are sitting right now, there is a sky unlike anything in our solar system. The sun in that sky is not yellow. It is deep red, the color of cooling embers, large and slow on the horizon. It barely moves. In fact, it does not move at all. It sits fixed at the same point in the sky, day after day, year after year, for billions of years. The ground beneath you has never seen a sunrise. It never will. But look up. Long pose, scattered across that sky, visible to the naked eye, are other worlds. Not points of light, not the pinprick stars you see from Earth. Actual disks, spheres. One of them shows swirling cloud formations you can almost resolve. Another has a pale blue tinge that might be ocean, or ice, or nothing at all. You can see 6 worlds from one, all orbiting the same small red star, close enough to reach out and touch with your imagination. This is TRAPPIST-1. It is 39.6 light-years from Earth. It has 7 rocky planets, all roughly the size of Earth. 3 of them sit in what scientists call the habitable zone, the orbital band where liquid water can exist on a planet's surface. And it is, by every measure we currently have, the most Earth-like planetary system ever found. We cannot go there, not in any human lifetime, not in any human civilization, not with any technology that currently exists or is likely to exist within the next century. But we can see it, we can measure it, we can decode it, light year by light year, photon by photon. And what we have found there in the last decade has changed the way humanity thinks about life in the universe, and about how fragile the conditions for life actually are. This is the journey to TRAPPIST-20, not the physical journey. That is impossible. The intellectual one, the one that right now is the only kind we can make. First, the scale, because until you genuinely feel it, nothing else in this story makes sense. The Earth is 150 million kilometers from the Sun, 1 astronomical unit. The distance from Earth to Neptune, the outermost planet, is roughly 30 astronomical units. That is the outer edge of our solar system in familiar terms. 1 light-year is approximately 9.46 trillion kilometers, 63,000 astronomical units. The entire span from our Sun to Neptune fits inside a single light-year about 2,000 times. TRAPPIST-1 is 39.6 light-years away. The fastest spacecraft humanity has ever built, Voyager 1, travels at approximately 17 kilometers per second. It has been moving continuously for 48 years. It is currently about 165 astronomical units from Earth, still inside our solar system by most definitions, still a tiny fraction of 1 light-year. At that speed, a mission aimed at TRAPPIST-1 would arrive in approximately 690,000 years. 690,000 years. The earliest anatomically modern humans appeared roughly 300,000 years ago. A mission launched today would arrive at TRAPPIST-1 more than twice the entire span of human existence from now. The civilization that launched it, the language it spoke, the goals it had, all of it would be ancient mythology to whoever or whatever might be waiting on the other side. The number is not a travel inconvenience. It is a war, a physical fact of the universe that does not care about our ambitions or our curiosity. And yet in 2016, a team of astronomers announced they had found not 1, not 2, but 7 worlds around this star, and the scientific community lost its mind. TRAPPIST-1 is not a glamorous star. It is an ultra-cool red dwarf. Its mass is just 9% of the Sun's. Its radius is only slightly larger than Jupiter's. Its surface temperature is approximately 2,550 Kelvin, compared to 5,778 Kelvin for our Sun. It burns so faintly that its total luminosity is only 0.05% of solar output. If you placed TRAPPIST-1 where our sun is, Earth would be a frozen rock. Mars would be a frozen rock. Even a planet at the distance of Mercury would struggle to stay liquid. It was catalogued in 1999 and spent the next 15 years as an unremarkable footnote in stellar databases. A dim, cool, insignificant ember 39 light-years out, too faint to see without a telescope, too ordinary to warrant attention. Then, a Belgian astronomer named Michaël Gillon pointed a small telescope at it. Not a famous telescope, not a billion-dollar instrument. The TRAPPIST telescope, the Transiting Planets and Planetesimals Small Telescope, a 60-centimeter mirror in the mountains of Chile. By modern astronomical standards, almost comically modest. In 2015, Gillon noticed something. The star's light was dimming on a regular schedule. Not catastrophically, not visibly to the naked eye, but with precise measurement. The brightness of TRAPPIST-1 was dropping by a tiny fraction of a percent, then recovering, then dropping again. On a different schedule, then a third. He was watching planets cross the face of the star, 3 of them at first. 3 rocky worlds orbiting this small red ember faster than Earth completes a single month. The innermost planet completed a full orbit in 1.5 days, the second in 2.4 days, the third in around 4 days. That was just 2015. In 2016, Gillon's team brought in larger instruments, the Very Large Telescope in Chile, and then the Spitzer Space Telescope in orbit. What they found ended any debate about whether this was a remarkable system. 4 more planets, 7 total, all rocky, all orbiting the same small star. The discovery paper was published in Nature on February 22, 2017. It became one of the most downloaded scientific papers of that year. NASA held a press conference. The system was described as the single best target in human history for the search for life beyond Earth. And for a moment, before the physics caught up with the excitement, it felt like we had found something. Now, forget the numbers for a moment. Forget the orbital periods, the stellar luminosity, the mass estimates. I want you to understand what this place might actually look like from the inside. Stand on TRAPPIST-1e. It is the 4th planet out from the star. Scientists consider it the most Earth-like of all 7 in terms of energy received from its host star, roughly 66% of what Earth receives from the Sun. Its estimated mass is close to Earth's. Its likely composition is rocky. If there is liquid water anywhere in this system, TRAPPIST-1e is where the models say it is most likely to survive. The ground beneath you might be basalt or granite or something without a name in any human language. The sky above you is not blue. The star is too red, too dim to scatter blue light through an atmosphere the way our sun does. If there is an atmosphere and it resembles ours, the sky is probably burgundy or deep amber or the color of a late autumn dusk that never resolves into night. The star itself, on the horizon, appears roughly the same apparent size as our sun does from Earth, but it is not white or yellow. It is a deep red orange, the color of a heating element approaching maximum temperature. And it doesn't rise. It doesn't set. It hangs in exactly the same position it has always occupied. The same point on the horizon, fixed, permanent, for the entire history of the planet. The day side of this world has always faced the star. The night side has never seen it. Now look east. There is another planet visible in the sky. Not a star, not a point of light, a disk, a sphere, large enough to show cloud formations to the naked eye. It is TRAPPIST-1d, the planet 1 orbit closer to the star. From the surface of TRAPPIST-1e, it appears larger than the full moon as seen from Earth. Look west. There is TRAPPIST-1f, 1 orbit further out. Smaller in apparent size, but still visibly a world. a disk, a surface, another planet you can look at and say, something might be happening there. On Earth, the closest planet to us is Venus. It never appears as more than a brilliant point of light. We have never, from any world in our solar system, been close enough to any neighbor to resolve its surface with the naked eye. In our solar system, the distances between planets are too vast for that. Here, at TRAPPIST-1, the planets orbit so tightly, so close together, that from the surface of any one of them, several others are visible as actual disks. You live on a world surrounded by other worlds you can see. If TRAPPIST-1a has an atmosphere and liquid water, wind moves across it, rain falls on it. Temperature gradients between the permanent day side and the permanent night side drive atmospheric circulation of extraordinary complexity. And between those two extremes, between the hemisphere of eternal day and the hemisphere of eternal night, there is a ring. A narrow band where the star sits permanently on the horizon, casting an unmoving twilight across the landscape. The terminator zone. This region is not scorched and not frozen. It is the boundary between worlds. If liquid water exists anywhere on TRAPPIST-1e, if biology has found any foothold at all, the models predict it would be here, in this ring of perpetual dusk, caught between a world of fire and a world of ice. That is what the physics allows. Whether the physics delivered it is the question we cannot yet answer. Now here is the problem. The same star that keeps TRAPPIST-1e warm enough for liquid water has been trying to destroy it for 7 billion years. TRAPPIST-1e orbits its star every 6.1 days. At that distance, about 4% of the distance between Earth and the Sun, the gravitational tidal forces are overwhelming. They have synchronized the planet's rotation to its orbit. One face locked toward the star, one face locked away, permanently. This is called tidal locking, and it has two major consequences. First, the obvious one we have already seen. No sunrises, no sunsets, no seasons, a permanent geography of heat and cold. Second, the less obvious but more catastrophic one, a planet that rotates once every 6.1 days, almost certainly cannot generate a strong magnetic field. Earth's magnetic field is produced by the movement of liquid iron in its outer core, driven partly by the heat of radioactive decay and partly by the planet's rotation. Earth rotates once every 24 hours. That fast spin, maintained over billions of years, generates a magnetic dynamo strong enough to deflect charged particles before they reach the upper atmosphere. TRAPPIST-1e rotates once every 6.1 days. That is 16 times slower than Earth. The dynamo that rotation can sustain is correspondingly weaker, perhaps non-existent, and without a magnetic field, the planet has no shield. TRAPPIST-1 is not a calm star. Red dwarfs are magnetically violent. Their plasma circulates from core to surface, generating tangled, powerful fields that periodically snap and release in catastrophic explosions called flares. TRAPPIST-1 is particularly active. It produces minor flares almost continuously, but it also produces superflares. In 2017, astronomers observed a single flare from TRAPPIST-1 that caused the star's brightness in ultraviolet wavelengths to increase by a factor of several hundred in under a minute. The planet TRAPPIST-1a was receiving that ultraviolet blast from a distance of 4% of an astronomical unit, not the 100% distance that Earth maintains from its star, 4%. 23 times closer than Earth is to the Sun. The radiation arriving at TRAPPIST-1a during a major superflare is estimated at hundreds to thousands of times the intensity Earth experiences during the most severe solar events in recorded history. X-rays, extreme ultraviolet, ionizing radiation that tears electrons from atoms and shreds organic molecules. The kind of radiation that, without shielding, does not damage living tissue. It ends it. Each major flare also drives what is called a coronal mass ejection, a vast cloud of superheated plasma hurled outward at millions of kilometers per hour. These clouds crash into a planet's atmosphere like cosmic shock waves, stripping gas molecules away and flinging them into space. Between flares, the stellar wind from TRAPPIST-1, much denser than the solar wind that bathes Earth, does the same work more slowly. Over 7 billion years, at 4% of an astronomical unit, with minimal magnetic protection, the atmosphere of TRAPPIST-1e has been under assault for longer than Earth has existed. The question is whether any atmosphere survived. In 2023, the James Webb Space Telescope turned its mirrors toward TRAPPIST-1, not at the habitable zone planets first, at TRAPPIST-1b, the innermost world, the most exposed. Before I tell you what it found, understand what Webb was actually measuring. The telescope cannot take a photograph of TRAPPIST-1b. At 39 light-years, it is far too small and far too close to its star to image directly. Instead, Webb measured the thermal emission of the night side of the planet, the infrared radiation leaking from the hemisphere permanently facing away from the star, by observing the system as the planet passed behind the star and disappeared. The logic is precise. If the planet has a thick atmosphere, wind and circulation distribute heat from the hot day side to the cold night side. The night side stays warm. If there is no atmosphere, the night side faces open space with nothing between it and the void. The night side is cold. TRAPPIST-1b's night side was cold, not a little cold, essentially as cold as an airless rock would be at that orbital distance, with nothing retaining heat at all. The data was unambiguous. TRAPPIST-1b almost certainly has no substantial atmosphere. 7 billion years of stellar wind and superflares had done their work completely. In 2024, Webb turned to TRAPPIST-1c, the second planet. Same result. Long pause. 2 of the 7 worlds, confirmed or near-confirmed bare rocks. The stellar bombardment had stripped whatever they once had, and these were only the 2 innermost planets. The most exposed, the most vulnerable. The violent history of their star had been running longest on them. Ooh. TRAPPIST-1e, F, and G, the habitable zone candidates, have not yet been characterized with the same precision. They are further out, less exposed. The models that allow for higher levels of geological outgassing to replenish a stripped atmosphere still leave room for something to survive there. We do not know yet what Webb will find when it looks at them. That uncertainty is not a failure. It is the most important open scientific question in planetary science right now. And Webb is still looking. So let us accept the best-case scenario. Let us say TRAPPIST-1e has an atmosphere. Let us say the geological activity of the planet has kept pace with the stellar stripping. Let us say liquid water pools in the terminator zone and chemistry has had 7 billion years to work. How do we get there? The answer is the same as it was for Alpha Centauri, with one critical difference. Alpha Centauri is 4.2 light-years away. TRAPPIST-1 is 39.6, nearly 10 times further. Every propulsion technology that might reach Alpha Centauri in a merely impossible time frame reaches TRAPPIST-1 in a truly geological one. Voyager at its current speed, 690,000 years. A chemical rocket at its theoretical ceiling, tens of thousands of years. The gap between interplanetary travel and interstellar travel that applied to Alpha Centauri applies here with 10 times the severity. The chemical rocket, the technology that took humans to the moon, that launched every deep space probe ever built, exhausts its physical potential at speeds that still require thousands of years to cross 39 light-years. The rocket equation, derived in the early 20th century by Russian pioneer Konstantin Tsiolkovsky, is brutal in its constraints. To go faster, you do not need proportionally more fuel. You need exponentially more. To shorten the trip from 690,000 years to 70,000 years requires a spacecraft where the ratio of fuel to payload is essentially infinite. The mass of entire planets converted to propellant for a single mission. Chemical propulsion is magnificent technology for reaching orbit. It is fundamentally incapable of reaching the stars. Long pause. If you cannot make the rocket fast enough, you reframe the problem. You accept the time. You build a ship that is not a vehicle, but a civilization. Picture a corridor 4 kilometers long. Metal walls, artificial lighting cycling to simulate a day that nobody aboard has ever actually experienced. Recycled air, recycled water, recycled everything. Because in interstellar space, there is no resupply, no correction, no second chance. Whatever the ship carries at launch is all it will ever have. In that corridor, people are born, they grow up, they have children, they die, without ever seeing an open sky or a natural horizon. Their children do the same, and their children's children, and on for 400 years. This is the generation ship concept. A spacecraft that is not a vehicle for an individual journey, but a container for a small civilization sustained across generations for the sole purpose of arriving somewhere its founders will never see. The engineering challenges are extraordinary. The closed ecological systems required to recycle water, oxygen, and nutrients perfectly for 400 years with zero margin for systemic failure. The radiation shielding, several meters of dense material required to protect inhabitants from the constant bombardment of galactic cosmic rays during the voyage. The nuclear reactors that must run autonomously, without maintenance, for longer than any reactor ever built on Earth has operated. The navigation and communication systems that must function without repair for generations. These problems are large. They are not obviously insoluble. Given sufficient resources and time to develop the technology, they might be addressed. The human problems are different. What does it do to a person to know they were born for a purpose they will never personally fulfill? To live their entire life in a metal corridor while the universe outside is lethal radiation and interstellar dust. To know that their contribution to the mission is simply to be born, survive long enough to reproduce, and raise children who will do the same. No human institution has ever maintained coherent purpose across 400 years without fundamental transformation. The Catholic Church is 2,000 years old, but is not the same institution it was at its founding. The United States is 250 years old and has already been through a civil war and multiple constitutional crises. A mission culture that sets out with a clear scientific mandate in 2050 would, by Generation 8, be subject to reinterpretation, schism, revolution, and the normal human tendency to prioritize immediate survival over abstract long-term goals. By Generation 15, the destination might be mythology. The people aboard might have evolved a theology around the star on the viewport and forgotten that the star was originally a target rather than a deity. The generation ship might arrive at TRAPPIST-1 as something its founders would not recognize. A floating ruin, a society that has been shaped by 400 years of closed corridor existence into something optimized for life aboard the ship, not for exploring what's outside it. The engineering is solvable. The sociology may not be. The nuclear era offered a different answer. Not accept the time. Attack it. Between 1958 and 1965, one of the most audacious engineering proposals in American history explored a deceptively simple idea. What if a spacecraft could be driven not by burning fuel, but by detonating nuclear bombs? Project Orion proposed exactly this. The ship would carry thousands of small nuclear pulse units in its magazine. One by one, they would be ejected behind the craft and detonated. A massive armored pusher plate at the rear would absorb each blast. Enormous shock absorbers connected the pusher plate to the crew section, smoothing each explosion into a steady, survivable acceleration. Scale models were built and tested using chemical explosives. They flew beautifully. The physics was sound. An Orion vessel accelerating over months of continuous nuclear detonations could theoretically achieve 5 to 10% of the speed of light. At 10% of light speed, TRAPPIST-1 is 396 years away. Still a generation ship, yes, still beyond any single human lifetime. But 396 years instead of 690,000. Project Orion was cancelled in 1963, not because of engineering failure, because the Partial Test Ban Treaty prohibited nuclear detonations in space. The project was shelved before a single full-scale prototype was built. The most powerful propulsion concept ever seriously designed for human space travel has spent the last 60 years sitting in archived documents in government libraries. In the 1970s, the British Interplanetary Society went further. Project Daedalus asked a single question. Could a fusion-powered spacecraft reach another star in a single human lifetime? The design was an unmanned probe aimed at Barnard's star, 6 light-years away. Its engine would fire pellets of deuterium and helium-3 into a magnetic reaction chamber 250 times per second. Each pellet would be compressed by electron beams into thermonuclear ignition, a tiny hydrogen bomb contained and directed by magnetic fields into exhaust thrust. The ship would weigh 54,000 tons at launch. 50,000 of those tons would be fuel. After 4 years of acceleration, it would reach 12% of the speed of light. The physics worked. The fuel did not. Helium-3 is extraordinarily rare on Earth. The study concluded that the only practical source of the tens of thousands of tons required was robotic mining factories in the atmosphere of Jupiter, technology that would need to be developed, deployed, and operated in the outer solar system before the mission could even begin. Daedalus remains theoretical, not because it was impossible, but because the infrastructure required to attempt it does not yet exist. In 2016, the same year the full TRAPPIST-1 system was announced, a different approach was unveiled. A consortium of scientists and philanthropists, including Stephen Hawking and Russian billionaire Yuri Milner, announced Breakthrough Starshot. Its goal: send the first human-made object to another star system within a generation. The concept dissolves the traditional idea of what a spacecraft looks like. Forget fuel, forget engines, forget crew quarters. Breakthrough Starshot proposes a chip, a wafer of silicon no larger than a postage stamp, weighing a few grams. Into that chip, nanoscale engineering would pack a camera, a communication laser, navigation sensors, and a power source. This nanocraft would be attached to a sail just a few meters across, thousands of atoms thick, made of metamaterial reflecting light with near-perfect efficiency. The engine that accelerates this sail would not be aboard the ship. It would be on the ground. A phased array of lasers, hundreds of them, combined into a single coherent beam aimed skyward from a high-altitude desert site. Total power up to 100 gigawatts, more than the combined nuclear generating capacity of an entire large nation, focused into a beam tracking a sail the size of a bedroom rug. The acceleration, tens of g-forces, impossible for a human body, irrelevant for a silicon chip. In 10 minutes of laser illumination, the sail reaches 20% of the speed of light. Long pause. At that speed, TRAPPIST-1 is 198 years away. A mission launched today could return data before the year 2224, shorter than the entire history of the United States, longer than any human life, but a time frame that human civilization can meaningfully conceptualize. None of the components of breakthrough Starshot violate physical law. The barriers are engineering barriers, not physics barriers. That distinction matters enormously. But there are two problems that have not been solved. The first is deceleration. A nanocraft traveling at 20% of the speed of light carries kinetic energy of staggering magnitude. It has no brakes. The laser that accelerated it is 40 light years behind it and cannot help it stop. Any conventional braking mechanism, thrusters, drag sails, would require mass that destroys the fundamental premise of a gram-scale probe. Long probe. As currently conceived, Breakthrough Starshot is a flyby mission. The nanocraft would pass through the TRAPPIST-1 system in approximately 4 hours. 4 hours to observe 7 worlds, then continue into the dark forever. The data it collected would take 40 years to reach Earth at the speed of light. Engineers have imagined alternatives, using the sails from TRAPPIST-1's own star to brake, deploying a magnetic sail against the stellar wind to decelerate. Each solution introduces mass, complexity, and failure modes that undermine the design. Some proposals work in principle, but would require centuries of deceleration. The ship would overshoot the system by light years before coming to rest. A mission that can truly stop at TRAPPIST-1 must carry its own deceleration fuel, and that fuel must shed exactly as much velocity as was gained during acceleration. In practice, this means a ship like Daedalus, twice over. One stage to accelerate, one stage to brake. The mass and complexity scale accordingly. The technologies that make fast acceleration possible make stopping nearly impossible. The technologies that make stopping possible make the mission almost inconceivably large. The first generation of interstellar probes will almost certainly be flybys, a glimpse, not a visit. The second problem is the universe itself. Space between the stars appears empty. It is not. The interstellar medium contains roughly 1 atom of hydrogen per cubic centimeter, a vacuum far exceeding anything achievable in any Earth laboratory. But it also contains something else. Microscopic grains of silicate, ice, and carbon scattered invisibly through the void. At orbital velocities, the speeds of spacecraft within our solar system, a grain of dust hitting a probe is a minor annoyance, a small crater in a heat shield. At 20% of the speed of light, the calculation changes completely. A grain of dust weighing 1 milligram, 1,000th of a gram, invisible to the naked eye, something you could not feel if it landed on your skin. Traveling at 60,000 kilometers per second, carries kinetic energy equivalent to approximately 400 kilograms of TNT. That is not a chip in the paint. That is an explosion that vaporizes the entire nanocraft in a burst of plasma. Even particles far smaller than a milligram punch through delicate electronics with the force of a rifle bullet. And at these velocities, individual hydrogen atoms become a radiation hazard. The spacecraft is flying into what amounts to a continuous particle beam, with billions of hydrogen nuclei striking its forward face every second, slowly sputtering away the surface material and generating secondary radiation that corrupts electronics and damages sensors. Over a 200-year flight, The cumulative damage from interstellar dust and galactic cosmic rays, high-energy atomic nuclei, accelerated to near light speed by distant supernova shock waves and streaming through the galaxy in all directions, could corrupt navigation software, flip critical bits in stored data, and degrade sensors past the point of usefulness before the probe arrives. The darkness between stars is not passive. It is a minefield. The faster you travel through it, the more lethal it becomes. We have arrived at a conclusion that looks, on its face, like an argument for despair. The destination is uncertain. 2 of the 7 worlds are already confirmed stripped bare. The habitable zone candidates might have atmospheres, or might not. The violent history of their star has had 7 billion years to work on them. The journey, with our current technology, takes 690,000 years. The best near-term concept, breakthrough Starshot, delivers a 4-hour glimpse in 198 years. If it works. Stopping requires technology we do not yet possess. The space between here and there is laced with dust that becomes explosions at relativistic speeds and saturated with radiation that erodes both silicon and biology. So why look? Slow. Why have scientists dedicated careers to studying this system? Why did a billionaire fund a laser sale initiative the moment the planets were announced? Why did the paper confirming 7 Earth-sized worlds become one of the most downloaded scientific documents of the year? Because TRAPPIST-1 is something we have never had before. It is a controlled experiment. 7 rocky worlds, same star, same age, same bombardment history, different orbital distances, different amounts of stellar energy received, different outcomes. 7 variations on the question of what happens when you put a terrestrial planet around a red dwarf and run the clock for 7 billion years. TRAPPIST-1b, stripped bare. TRAPPIST-1c, stripped bare, or close to it. TRAPPIST-1d, smaller, drier, hotter, status unknown. TRAPPIST-1e, the best candidate, still under investigation. TRAPPIST-1f, further out, colder, would require a greenhouse effect to maintain liquid water. TRAPPIST-1g, even further, possibly icy. TRAPPIST-1h, the outermost, almost certainly frozen. 7 experiments in habitability, run simultaneously, with results we can measure from 39 light-years away. Each planet that fails to have an atmosphere tells us something about the process of atmospheric stripping around red dwarfs. Each planet that does retain one, if any do, tells us about the geological processes that resist it. The full picture, when Webb finishes its survey of this system, will be the most detailed comparative planetology study ever conducted outside our solar system. And what it is already telling us has profound implications for the search for life elsewhere. Red dwarfs are the most common type of star in the Milky Way. They account for approximately 70% of all stars in the galaxy. If red dwarf systems can harbor habitable planets, the number of potentially life-bearing worlds in the Milky Way is enormous. Billions, perhaps tens of billions. If they cannot, if the combination of tidal locking, stellar radiation, and atmospheric stripping makes habitability effectively impossible around red dwarfs, then the universe is a significantly lonelier place. The habitable planets would cluster around the rarer, calmer, G-type stars like our Sun, the same stars that make up only about 7% of the stellar population. TRAPPIST-1 is the most powerful test of this question ever attempted. And it is also, unavoidably, a mirror. Because when you look at the conditions that make Earth habitable, a G-type star with a stable, low UV output, a planet at just the right orbital distance for liquid water, a strong magnetic field generated by a fast-rotating iron core, a thick ozone layer maintained over billions of years, a large moon that stabilized the planet's axial tilt and prevented runaway climate oscillation, a geological cycle that regulates atmospheric carbon dioxide over geological time. When you list all of those conditions and recognize that every single one of them is necessary, and that TRAPPIST-1's planets appear to lack several of the most critical ones, you understand how improbable we are. Not inevitable, not typical, a very specific set of conditions, each of which could have been otherwise, each of which in this system appears to have gone wrong. Our Sun is not an average star. It is a calm, stable, middle-aged G-type star in a galaxy full of violent red dwarfs and giant blue supergiants. Our magnetic field is not generic planetary equipment. It is the output of a specific interior structure, a specific rotation rate, a specific composition maintained over 4.5 billion years. Our atmosphere did not persist by default. It was protected. We are, by everything TRAPPIST-1 teaches us, an exception. In the next 3 to 5 years, James Webb will complete its atmospheric survey of TRAPPIST-1 E, F, and G. Long pause. If it finds water vapor and carbon dioxide in the transmission spectrum of TRAPPIST-1 E, the signature of an active water cycle, there will be no immediate scientific consensus that the planet harbors life. Those gases have non-biological origins. But there will be a debate unlike any in the history of science, a debate conducted in real time on a planetary scale about what we might be sharing the universe with, about whether the biosignatures that follow, oxygen, methane, ozone, when Webb or its successors look for them, will confirm what everyone will already be wondering. If Webb finds nothing, airless rocks all the way through the habitable zone, the conclusion is quieter but equally important. It would mean that the combination of red dwarf radiation and tidal locking is almost universally fatal to planetary atmospheres, that life around the most common type of star in the galaxy is not just unlikely but essentially impossible, that we need to look elsewhere, that the search narrows. Either answer changes the direction of the search for life in the universe. Either answer was worth every photon we have collected from 39 light years away. There is a version of this story where TRAPPIST-1 is only a disappointment. The nearest ones are rocks, the others are unknown. The journey is impossible. The star is violent. The physics will not cooperate. I don't find it disappointing. I find it clarifying. The 7 worlds of TRAPPIST-1 are not failures. They are data, 7 data points about what the universe does to planets around the most common kind of star over the longest timescales we can currently study. That data is changing our models of planetary evolution, atmospheric physics, the limits of habitability, and the probability of life beyond Earth. It is doing this right now, in laboratories and university offices and conference rooms, while the Webb telescope quietly collects more photons from a dim red star in Aquarius. And we are 39.6 light-years away from those worlds. We will not reach them in any lifetime we can currently imagine. The laws of physics have made that clear. But the idea that they are beyond our understanding, beyond our reach in any meaningful sense, that was already wrong the moment a Belgian astronomer with a 60-centimeter telescope noticed a star blinking. We decoded those 7 worlds from here, from this distance, with these instruments, with the ingenuity of a species that has been doing science for roughly 500 years and space science for less than 70. That is not nothing. That is possibly the most remarkable thing we have ever done. I want to ask you something. James Webb will give us an answer about TRAPPIST-1a within the next few years. We will know, with reasonable confidence, whether it has an atmosphere or not, whether it has water, whether any of the 7 worlds around this violent red star retained something worth calling habitable. If the answer is yes, if one of those worlds has an active water cycle and an atmosphere that has survived 7 billion years of bombardment, what does that change for you? About what we are, about how alone we are, about what comes next? Comment below. I'll read every one.